Hello, everyone, and greetings from Greece. My name is Nikos Charalampidis, and today I'm going to present to you a new family of chaotic maps constructed using chirp signals. The creation of new chaotic systems and methods for generating them is very important in many scientific and engineering domains. Different applications require different characteristics of chaos, making a one size fit all approach very impractical. For example, in encryption systems, they have to maintain chaotic behavior over large parameter ranges to ensure robustness and resistance to attacks. While other areas, for example, modeling natural systems or engineering phenomena, may prioritize a richer variety of dynamical phenomena for modeling or analysis. Now, to meet these needs, researchers develop and refine systems through what we call hautification, the process of constructing new chaotic models or enhancing existing ones. These methods can increase the parameter range of chaotic behavior, remove fixed points, eliminate periodic regimes, or even introduce multi-stability and improve robustness. Now, the resulting systems can be tailored to specific requirements, whether for computational efficiency, hardware implementation, or physical modeling. Hautification techniques employ diverse mathematical transformations, including trigonometric, exponential, nonlinear, piecewise, and modulo-based functions. Such approaches have produced systems with robust chaos, no coexisting attractors, and complex dynamical structures. Now, these properties expand the practical utility of chaotic systems, enabling advances in encryption, secure communications, optimization algorithms, and the simulation of complex natural processes. So, as you can see, there is a constant need for new chaotic systems. Our paper, our work builds on recent contributions to chaotic modeling by developing a method for generating discrete dynamical systems based on chirp signals, which are inspired by signal theory. Uh, so, chirp signals are waveforms whose frequency changes over time, either increasing or decreasing or varying non-linearly. They're widely used in radar, sonars, and communications because of their controllable frequency sweep, and that's why many refer to them as sweep signals. Here we are interested in their mathematical flexibility, since their time varying nature can introduce complex, even chaotic behaviors when used to generate maps. Now, to understand chips, it helps to think it in terms of the instantaneous frequency. The rate at which the phase of the signal changes. By controlling how this frequency evolves, we can shape the signal's dynamics. In our work, this control becomes the bridge between a continuous time chirp and a discrete chaotic map. So, for different instantaneous frequencies, we can generate different types of chirp signals. Now, there are many kinds of chirp signals, linear, exponential, logarithmic, and more exotic ones I can imagine. So, here we can see a linear chirp signal produced from a linear frequency, and below we can also see an exponential chirp signal produced by an exponential frequency. Each of these forms produces a unique temporal pattern, and those patterns translate directly into how these resulting maps behave. Some give smooth oscillations, others yield sharp transitions or bursts. So, from chirp signals to discrete maps, the key idea in this research is transforming a continuous chirp signal into a discrete time map. By sampling or iteratively applying the chirp space function, we construct a map that preserves its nonlinearity. This approach allows us to build a family of chaotic maps with tunable complexity simply by adjusting chirp parameters like amplitude and the control parameters of the instantaneous phase. Now, to confirm whether a system is truly chaotic, of course, we use the Lyapunov exponent, and as we all know, the Lyapunov exponent measures how fast nearby trajectories diverge. Essentially, how sensitive the system is to initial conditions. A positive Lyapunov exponent implies chaos, while since small differences quickly become unpredictable, and if we have negative Lyapunov exponent, this means periodic behavior. Now, we have computed the Lyapunov exponent of this family of maps, and we have it in three terms. This is the first term, the cosine term, the constant ln a term, and the term that's where the derivative of the instantaneous phase is included. So, what we can have as a result from this? The first thing is that because the absolute value of the cosine is always less or equal to 1, we have that the first term, the cosine term, will always be at best 0. Otherwise, is always negative. Of course, this doesn't imply that the Lyapunov exponent of a chirp signal is always negative. We can actually have positive Lyapunov exponent values for from the chirp signals by controlling the parameter A, and of course, controlling the parameters that are inside the derivative of the instantaneous phase. Now, if we can further analyze this expression and substitute the cosine in this way, where vi is a positive floating point with integer part from 1 to 9, and di is a positive integer value, we can have this expression here, which we introduce it as kappa delta kappa plus delta plus gamma. Kappa is this term, and this term actually is always positive, but it's not controllable term. So we are not interested in this term. This term is always a negative term, and we don't like this term. We have to compensate for this term. And gamma is the actual term that we can control by controlling the parameter A and, of course, the parameters of the derivative of the instantaneous phase. And by controlling these parameters, we can actually compensate for the negative term. Now, it's very important to realize that because the reduction in delta outpaces the growth of gamma, it may be possible that we have to increase the values of the parameters in the derivative of the instantaneous phase in order to be able to generate robust chaos and consequently large regions of constant chaos. So to see this in an example, we show here an illustrative example by using a linear chirp signal. So essentially, we used a linear frequency in order to produce a linear chirp signal. And here you can also see the Lyapunov exponent of this map. So what we can see is that here in this term, we have are included the kappa and delta term. And here the rest is the term that we can actually control. So and we control it by controlling A, M, and C. And here is actually very interesting because if we set M to be equal to 0 and C to be 1.5, then from through this map we can have the sign map, which is a special case of the map that we introduce, we show you here. So by using classical tools for investigating the dynamical behavior of chaotic systems, namely bifurcation diagrams and Lyapunov exponents. What we can see here is that the map exhibits the classic route to chaos through period doubling. And as parameters increase, the system's oscillations double in period until they become chaotic. We also observe periodic windows, intervals where the system briefly regains regular behavior before chaos reemerges. And these transitions highlight the rich and complex structure uh, of nonlinear systems. Uh, Now, uh, what we see here is that when we increase parameters like the amplitude or the modulation constants, the chaotic regions become more dominant and robust. The bifurcation and Lyapunov diagram show that here and make it clear that larger values produce more continuous regions of chaos with fewer stable periodic islands. This demonstrates that the chirp-based formulation allows precise control over the strength and persistence of chaotic behavior. Now, here, what we show you is essentially Lyapunov exponent diagrams with respect to two parameters. This part actually confirms that the chirp-based maps are highly sensitive to initial conditions. Tiny changes leads to vastly different outcomes, defining property of chaos. The computed Lyapunov exponents align closely with our theoretical expectations, namely that when we have higher parameters, the system becomes more unpredictable, having larger Lyapunov exponents and expanding its chaotic regions. So, interpretation of these results. We see that the chirp-based maps successfully combine mathematical tractability and with dynamic richness. The analytical predictions match the numerical findings, showing that this approach gives both flexibility and control. By tuning these parameters, we can finally adjust the chaotic behavior, something that's difficult to achieve with traditional map constructions. Now, the advantages of chip-based maps. The first is that they are bounded maps with high variability. In example that I showed you, also a well-known map like the sign map is included as a special case, and it enables design of robust chaotic systems. Possible extensions of this work will be to design higher dimensional chirp maps, compose with other functions for general codification, or study dynamics in the extended map families. Now, potential applications of these maps can be in cryptography, secure communications, random bit generators, modeling complex nonlinear systems, and optimization algorithms in natural process simulation. To sum up, we introduced a chip-based family of chaotic maps. We derived an analytical Lyapunov exponent expression. We identified robust chaotic behavior regions. So, to conclude, the chirp signals provide a versatile foundation for chaos generation. Analytical and numerical results confirms rich dynamics, and we are very interested to investigate how to generate multidimensional maps and apply them to cryptography. Thank you very much.